So welcome everyone in person and online. This is our second sort of double feature by Yuan-Sen Ting. So Yuan-Sen got his PhD at Harvard, working with Charlie Conroy. Then he did a postdoc at Princeton, like a three-way postdoc between Google Fellowship, Carnegie, Princeton, IAS Fellowship. And then he went as faculty to ANU. And after being there for a few years, he decided to come back to the US, and now he's faculty at The Ohio State. And so today he's going to tell us about transcending the limits of astrostatistics with deep learning. Thank you.
Okay. Thank you for the invitation, and it's great to talk about again. So as I promised yesterday, today will be slightly more astronomy, like a lot more astronomy. But I also see a lot of grad students here, so I think the topic will be quite relevant just to have a broad exposure on what we call astrostatistics and why deep learning is changing the field of astrostats. Let's just start with the obvious thing, which is we live in a very different time. The younger student might not notice that not too long ago, we tend to collect one spectrum at a time. And we have a very small number of data set. Of course, this has drastically changed in the last 2 decades, where, for example, in the spectroscopic survey, we have the spectrograph, and this, of course, has changed how we do astronomy. So a big part of the astronomy nowadays quite often comes down to understanding the holistic distribution of stars and galaxies and photons all across the sky, right? And it has so long known that looking at the sky holistically can tell us quite a lot about the physics that engender the universe that we live in. A shining example of that will be the large-scale structure. So you probably have learned that in your cosmology classes. When you have a distribution of galaxies, the distribution of galaxies do not just form a white noise. They form some patterns, and if you can understand the patterns they are created by this distribution of galaxy, we can start to constrain the cosmological parameters. And this, of course, quite relevant because Euclid just has their first data release. Of course, the Roman is coming online, and then they have the DR2. These are all kind of in the same context, trying to understand the patterns that are spanned by the galaxy. But this, of course, this idea that you should be able to quantify the patterns that tell you about the physics is so profound that you want people, I believe, the Nobel Prize in 2019. And of course, this type of idea of looking at the pattern is everywhere in astronomy now. For example, beyond just the large-scale structure, if you think about reionization, it's the same idea. We are using the radio dishes of SKA to look at the 21 centimeter maps. The idea here is that, of course, different condition of the universe in the first 100 million years or so will have different patterns. If you can quantify the patterns, then you can start to understand what is happening in the first 100 million years. Classically, this type of pattern recognition is really mostly in cosmology, but this is no longer true. So in my earlier career, I also looked into, for example, the phase-based fluctuation of star and the chemical fluctuation of star. This is the same idea because we have a lot more data now in stars. So not only we are looking at the distribution of galaxies, we are also looking at the distribution of the properties of star. So all these are the same question as asking, well, if I have some observation, how do I understand the physics, the universe that we live in? And all this comes down to variation and statistics. We do variation of statistics in astronomy just because we live in one universe. You cannot do a frequentist in most of the cases. So what the Bayesian said is that as long as I can quantify my prior and my likelihood, I should be able to update my belief of the universe. So if I can describe what is the chances of observing what I observe, I should be able to update my belief of the physics based on the observation. So for people that have not worked extensively in statistics, I love to explain to students. You think about this as a simple example, how do you constrain the price of a car that you see in Austin if you have not only see the car for the first time? You need 2 things. What is the range of prices that you think that people can afford here? that's your prior. You also need a model, like can be a simulation that tell you given any prices, what are the type of car that you can buy, right? So if you have these two ingredients, of course, to get the posterior of the car, it's just a reading off from the likelihood. It's just to say that if I know Px given y, I should be able to get Py given x. So this is what base a theorem say. So like astrostatistic is like nothing more, like nothing less. This is one simple equation. But of course, this is like a bit simplistic. The challenges that we have faced in astrostatistics really come from the fact that it's really hard to quantify the likelihood. In many cases, the likelihood can be extremely complex, right? So if you take a simple example of just an image, a 512 times 512 image, then we are talking about a conditional distribution of about 25,000 a dimensional space. So this is why if you think about like the regime that we do like statistics in astronomy, it has been quite unlimited. It's really hard to see the background here, so there should be like some brown point, but the cyan point here show you the paper on Astro PH that uses a statistic, and this is a large language model, but these are just some keywords count, and you project the paper into a 2D concept space. If you squint your eye, then you see there are like three strongholds of astrostatistics in astronomy, meaning cosmology, pulsar, and exoplanets. And this is not too surprising because these are the three regime where analytic theory is still possible. If you think about pulsar, the physics is extremely clean. Exoplanet transit, the observation is extremely clean. That is the theory. Cosmology, if you go to the early universe, you can do a perturbation theory. Because the physics is clean, meaning that you can write down a very compact likelihood. If you can write down a compact likelihood, then you can do your statistic. Interestingly, I should also point out that these are also the three regime that actually won the Nobel Prize. So if you want to convince your colleagues outside your field that you know what you are doing, you better know how to do a statistic correctly. Unfortunately, meaning that like a lot of the domain that we care about in astronomy, historically, it's really hard to do a statistic, right? Not because they are not interesting, because they are too interesting, right? So things like star formation or galaxy evolution, things are becoming super nonlinear. We know how to simulate them, but it's very hard to write down a analytic likelihood. So this is why, like historically, if you think about astronomy, they are seemingly have a bifurcation of two fields. Now, on the one hand, you have cosmology, they are more like particle physics, and you have the rest of like astronomy, right? And in fact, in some of the departments, it physically like bifurcate into two sub-departments. And this is because in some of the astronomy, it's more like particle physics. The likelihood is easy to write down. You can do proper statistics. When the other regime, things become more non-Gaussian and non-linear. It's very hard to write down the likelihood. And people will just say, we can hope to wave our hand and have some qualitative understanding of the system. So this has been like the status quo of astrostatistics for a long time. So what has really changed in the last 5 years is that deep learning can do lots of things, but one of the things that it do extremely well is being able to bridge this gap to understand how we can trade some of these very complex and nonlinear systems with proper inference. So this is also like exactly what I have been doing for the last decade. So there are two lines of study that I have been like pushing in astrostats. So one is what we call now the mathematics of information. So trying to understand the theory behind deep learning. And the other is more brute force, but it's also becoming more and more like popular. It's using Gen AI to do what we call the simulation-based inference. So ultimately, what you try to solve is understanding how you can describe a very high-dimensional likelihood. So if this makes no sense for you for now, don't worry, because the next 40 minutes, the goal is to walk you through a little bit about what is the key idea of each of this. So, any question so far? I treat that as a lecture because there are so many grad students. Okay, so first of all, there's a mathematics of information. So So how should you think about data analytics? There are like a lot of big idea about big data and data analysis and about like machine learning. But what we really care in data quite often can be decomposed into two axes, right? You have on the one hand the true complexity or the information of the data, and the other is the informative part, the stochasticity of the data. So what do we mean by that? So let's put some data on this chart. So let's say I take the simplest observation in astronomy, which is the light profile of a elliptical galaxy. So this object, if you take the data by itself, might seems to be a n pixel vector because it has an n pixel from this image. Like it might seem to be a very high dimensional system. But for the longest time, we know that the light profile can be also described by a parametric form that we call the stochastic profile, meaning that I know how to represent the image in a much lower dimensional space. So if I can capture this tree number that we call B, the N, the R star E, I would have mostly capture the information from the light profile from the image. Of course, there are systems that are more complex and more stochastic. Again, my needs play a role. So you have the merger system. My needs is definitely more complex and also definitely more stochastic. You might ask, what do we think about? What do we mean by doing like data analysis? Quite often, when we think about data analysis, is really trying to do this top-down projection. So you try to find a compression of the data that you can live in a low dimensional space. And we want the data to live in a low dimensional space because we want to describe the likelihood. So a lot of the physical modeling is trying to compress out this informative part of the data. So how do you do this, what we call physical modeling? So for individual objects, the process is quite straightforward. Quite often you are trying to understand the symmetry of the data. So for example, the image of the elliptical galaxy will contain the orientation of the galaxy, but the formula from the stochastic profile will lose this information. Because the reason here is because the orientation of the galaxy do not really pertain any information, like physical information about the system. And this is why when you try to project out the information, you try to get rid of some of these symmetric groups from the data. So this is why like the symmetric groups and physics has really strong ties like historically, because it's just a very effective way to go from high dimensional the observation to low dimensional representation. So far so good. Right. This one object. The challenges with astronomy is that like when you zoom out from one object to the whole sky, which is what we alluded earlier. This is where the information lies, that a lot of the modern data astronomy looking at the sky as a whole. Meaning that we are not looking at individual objects, but rather we are looking at patterns that are spanned by the photons, the galaxy, and the stars. And in this case, this is what we call a stochastic field. The question is, how do you really quantify the stochastic field? So unfortunately, to quantify a stochastic field is a very, very difficult process. Perhaps the only thing that we know exactly how to do is a Gaussian process. So a CMV is a Gaussian process. You probably have learned that in your cosmology classes. You can think about a Gaussian process is the infinite dimensional extension of a Gaussian distribution. So just like a Gaussian distribution, you can fully characterize that with the mean and the variance. And the Gaussian process is also fully characterized by the first and the second moment, right? So the second moment in the stochastic field is the power spectrum. So this is why for a Gaussian process is fully characterized by the power spectrum. Unfortunately, the universe is not Gaussian, except for the initial condition. So as the universe continues to evolve, more and more substructure will appear, and things become more and more non-Gaussian over time. The question is, how do you find a low-dimensional representation of a non-Gaussian field? You can say, well, we can brute force and just use the power spectrum. That's one way to do that. But using power spectrum, you can compress the stochasticity, but you're also losing out a lot of the complexity of the maps. Why? I can tell you that these two maps have exactly the same power spectrum. But of course, they are very different from each other. So most of the non-Gaussian field, you cannot fully represent the patterns just by the second moment. Right? So what do you do? So people have come up with many human heuristic over the last few decades to how to quantify that. But because of deep learning become really popular, and they has been very successful, right? So there must be some mathematical connection that what the deep learning is doing that we can learn from. So this is what we call the mathematics of information. This is the big field in mathematics. It now called, I think at least a few years ago, it has the name of geometric machine learning, and then become like the mathematics of information. The name changed quite a bit, but after all, what they try to understand is why do we need to do a certain operation to do the signal processing? So take the particular example of the convolutional neural network. If you take a graduate level of machine learning courses, the lecturer will say, well, this is something that you should do. You put in an image, you just do convolution, nonlinearity, and averaging. This is magic, right? You just throw in the ingredient, convolution, nonlinearity, and pooling, and some magic will happen. Sorry. The question is that just a pure alchemy? Or is there way to mathematically understand why you should do this operation? It turns out that the answer is actually the latter. So there is actually a very deep mathematical understanding of a convolutional neural network. And to start to understand why convolutional neural network works the way it is, one can just go back to this question that we asked earlier. These two maps have the same power spectrum. Why the power spectrum are not capturing some of this structure and information from the patterns? So of course, it's really hard to understand a stochastic field. So in the colloquium, I tend to simplify that to an image of one pixel, thinking that you have one random variable. So you have a set of image. Each of these images has only one pixel. And this set of images will form a distribution. So X is drawn from P of X. And your task to come up with the summary statistic as if now if I take away this picture, now you can tell your friends next to you 3 numbers, such that in his or her mind can reconstruct the distribution. So what are the numbers that you would give your friend? I think about that for 5 seconds. So I think most of us, the number that you would give the first time is the variance, right? So if I tell my friend how fat the distribution is, then your friend will have a good understanding a little bit of what the distribution we are talking about. But of course, just giving the variance of the distribution actually do not tell your friend much. Why? Because you are missing out the tail, right? A lot of the information is in the tail. For example, your friend will not know if the distribution has a long tail or not. Unfortunately, in astronomy, most of the information is actually at the tail, right? You can ask why the universe become more and more non-Gaussian over time. The universe become more and more non-Gaussian over time is because of gravity. And gravity forms structure, and the structure will become bright pixel in the image. So this is why most of the information actually lies in the tail of the distribution, which is why some of the older cosmology people also use the halo mass function, or X-ray cluster, and radio cluster to probe the massive end of the distribution, because this is where the information lies. Because the second moment, the power spectrum do not capture the tail, and therefore it loses the information. So you can say, okay, so what do we do? So when I teach a astrostat classes, of course I will start by saying that, if you have a distribution, if you want to come up with finite numbers, there is this concept called the moments. So you will calculate the statistical moments, and this number tends to be very useful to understand the distribution. In face value, this seems like to be a good idea. Why? To remind you what is taking moments. Your statistic 4,000 level courses. You take the distribution, you multiply that with x to the power n, and then take the expectation. This is a very useful operation because as you multiply the distribution by x to the power n, you're amplifying the tail. right? This is why when you take a higher order moment, the tail of the distribution will contribute more. Why? Take the example, if you ask, what is the mean wealth of US? Most people will contribute. But if you ask, what is the wealth to the power 10 and the expectation, then Elon Musk and Jeff Bezos will pull away the weights because the billion to the power 10 will carry all the weights. Right? So this is why the higher the order moment tend to give more weight to the extreme object, and therefore by definition you should be able to capture the tail. But there is a problem with this kind of thinking, right? So this is what cosmologists has been doing for many decades. But this kind of thinking is very easy to see what is the problem. The problem is that when you're putting so much weight to a few galaxy or a few people, it's very easy to have the sampling noise. If you miss the estimated Jeff Bezos wealth by 5%, your 10th moment will be extremely off because you are dominated by that one person. So as you are amplifying the tail, you are amplifying the sampling noise. So that has been the problem for cosmology for a long time. So you would say, if I just have this simple case of a 1D, what should I do? What are the numbers that I should give my friends? There is actually a better way to do that. That's looking at lower order operation, right? So I'll give you a set of the operation, just bear with me. And you will see this number actually is quite useful. So for example, I have a distribution. I can first calculate the mean of the distribution. So this gives me a number. I call it S in the G0. And then we'll do some operation that is a non-linear. It's either sublinear, but also, the important thing is not super linear. So let's say I subtract the mean and take the modulus. So this is equivalent of the subtracting with respect to the mean and then forward. So this gives you another number, another transformed random variable that you call x1. And then you take the expectation, this gives you the second dashed line. And then you repeat the process. So this will give you a set of lines, but you are not giving a higher weight to the tail. But this gives you a way to quantify the distribution without expanding the sampling noise. You might wonder, isn't this a colloquium about deep learning? Why do I talk so much about math? If you have followed what I have said in the last 5 minutes, you would have mostly understand why convolutional neural network works. Because the convolutional neural network is also successively doing some sublinear operation with some pooling. Of course, they also do the convolution, which is the hard to explain in 5 minutes. But the point here is that all this CNN is very analogous in high dimensional space, trying to fold your distribution in a stable way so you can successively access to the higher order moment information of the data. This explains a lot of things that might seem to be voodoo magic at first. For example, if you train a CNN, your lecturer might say, use the activation function called the sigmoid function. Have you asked your lecturer, why not a polynomial? Why not a quadratic function? Why not a cubic function? The reason is because if you use a super linear function, then you're going back to do a higher order moment operation. In that case, you will expand the finite sampling noise. It's exactly because you are doing sublinear operation, like sigmoid function or tangent function, you can build deep learning models. So you can stack up many operations, and you're just successively accessing higher and higher order information from the data. So great. So this is if you understand some of the chemistry a little bit from the alchemy, then you would not need to rely on the alchemy. You can just use the chemical principle to design some of these signal processing tool to understand how to decompose the stochastic field. So this is something that I started to work a little bit during the COVID time, where a student and I and some colleagues at Johns Hopkins started to look into what we call the scattering transform, which I believe now become quite a popular tool. The idea is that we understand some of this operation and how it works. You can just design some analytic operation to decompose the stochastic field and come out with low dimensional representation that will capture the non-Gaussianity. So this all seems nice. It's mathematics, math and theory, but you also have some real life consequences. So we actually apply this idea to a range of topics that we care about in astronomy. First of all, is weak lensing. So just remind you what is weak lensing. So the idea here is that you want to quantify the dark matter. Of course, you don't see the dark matter, it's dark. So you need use a background galaxy and look at the shape distortion due to the dark matter and try to understand the cosmological parameters. So it has also long known that weak lensing maps, for example, with Roman and Euclid, is a very strong, can give you a very strong constraint on cosmological parameters like sigma A and omega n. But if you're just looking at, for example, here, if you just look at the power spectrum, then you will not be able to distinguish that. So if you run the simulation and looking at some of the big lensing maps, then will actually look quite different, even by eye. Hopefully, even at this low resolution, you can see that. Is that when you have a higher sigma 8, you have more bright spot compared to the lower sigma 8. Because as you change the sigma 8, you actually change the structure of formation, you have more structure form. But most of this structure form will populate the tail of the distribution. So if you use a second moment, you are not accessing the tail, and therefore you have a degenerate constraint. So now when we first proposed like a scattering and transform, we look into looking at weak lensing. So this is work done by Sihao Chen, who is now at the IAS, me myself, Chris Monard, and people. We show that this case of a scattering transform can give you a much stronger constraint in weak lensing. When we do that, it's just like like mathematically quite beautiful. Like seemingly there's something that we know how to do better than bispectrum and trispectrum. If people are in cosmology, you know that this has been really quite a standard, one of the standard alternate statistic now. It's only like in a few years because it's so clean and we understand what we are doing. So when you understand the chemistry, you do not necessarily need to rely on the alchemy. The other thing that we have started to work on more is, so one of the limitations why we want to understand the math behind deep learning is that deep learning will require a lot of training data. In many cases, you will not have that many training data. So if you understand the signal processing, then you can do with much smaller training set. So one topic that caught my attention in the last 2 years is the parity violation. So this is a question that people love to ask, meaning that if I flip the universe, is the universe statistically the same? This is a regime where the simulation is expensive, there are not that many simulations, and you also ideally want to work directly with the data. So this is in the regime where training deep learning becomes quite difficult. So this might seem to be a simple question, but it's not. For example, these two maps, one is a parity violating and one is not. One has more right-handed L than the other, and the other has the equal number of left-handed L and right-handed L. So in the last few years, I'm working with people, including at Ohio State, also with people in Queensland, with a student back Craig, that actually we look into how we can quantify parity violation better in simulation with a scattering transform. So this is as a function of number of training set, the significance that you can get. So the scattering transform can actually get a much stronger detection on the scattering transform. The next step is to apply that to data, but of course people who follow this field also know that there has been a lot of proof to say that the parity violation being claimed is likely not correct. So we decided not to pursue that. But still, the idea still stays. In this very big signal regime, you can actually look into some mathematics behind deep learning to do a much better quantification of patterns. By the way, Matt is also joining JPL as an MPP fellow, so he will be in the US. So he's now still in Australia. So this is one thing on cosmology, but I also want to show you that this is not just one trick pony. Like if you do work on the cosmology, actually you can, yes, because it applies to everything. When I was in Australia, they forced me to work on SKA because else they will bar me to enter the country. So I looked into the 21 or 70 meter with a postdoc. It's the same idea here. You have different physical condition. It's possible to stimulate the system. For different condition, you will see very different patterns. But the question is, how do you mathematically describe such a patterns? This is perhaps even more important because reionization is actually very far from being a Gaussian process. So if you want to say what is the processes that is closest to, mathematically is called the Levy process. So this is why if you apply some like alternate statistic to reionization, you get a much stronger gain than just like that big lensing. And also reionization is one of the regime where people have really hung out with the power spectrum for some reason, right? So we also show that for some of the data we collect now, the best way you can look for signal of reionization is actually through alternate statistic. Else it will still be most likely be buried under the sampling noise. So it's fine. You will say, well, I'm here to learn about deep learning. Here we come. So we talk about not just the theory behind deep learning, but some brute force deep learning. Still the part, the alchemy. So this is the second part. I want to use the last 15 minutes to talk a little bit about Gen AI, to talk about simulation-based inferences. So let's take a step back to go back to the drawing board, right? So we do a lot of this like mathematics. It really comes down to the question of doing the statistic. And we want to compress that to a representation because we believe that the high dimensional likelihood is very hard to quantify. But you can say, is that even necessary, right? Like, why not just describe the likelihood as it is? If you ask this especially a decade ago, but especially even 5 years ago, most likely you will be laughed out of the room because again, your observation can be easily millions of a dimension for an image or like tens of thousands of dimensions for a spectrum. And this was a really hard problem in the past, but things has changed. And the reason that things has changed, especially in the last 5 years, is because of Gen AI. We talk about Gen AI all the time. But you might wonder, what is the connection between Gen AI and a statistic? To understand the connection between Gen AI and statistics, one needs to know what Gen AI is. First of all, now let's live under the rock. Gen AI means that you give a prompt and you can answer you with some responses. In principle, it can give you all the answers that will satisfy the prompt. For example, here, making a kangaroo that operating telescope, you even capture a tourist that look into the telescope in the wrong way. So what is Gen AI? So ultimately what Gen AI is learning a high dimensional distribution. So thinking about how to make images, you will download some training data from your Instagram. You have some caption, you have some images. And what Gen AI try to do is try to capture the distribution of the data. Unsupervised, they're trying to find the contour, the distribution that capture your training set. Because once you have captured the distribution in X and Y, then to generate is not that difficult because you just think that for any given X, I want to generate all the possible Y. Or put it simply, all the Gen AI that we talk about are really trying to learn a high dimensional distribution. This is of course very schematic. If you think about text prompt and images are all millions of dimensions. But similarly, people are doing pretty well, right? Like all this Gen AI too, meaning that it's possible to learn a high dimensional distribution. So if you start to see the connection, then you realize that this is the dream of a statistician, because for the longest time we cannot do a statistic for very complex system. Is exactly because we cannot capture a high dimensional likelihood. So now we have a surrogate to do the likelihood, and therefore we can capture the other posterior. If this seems like too mathematical, you can just think about instead of having text prompt and images, now you have some cosmological parameters. So each time you run a cosmological simulation, you put in a certain X, your output gives you a Y. So you have many tuple X and Y. So if you capture the distribution of X and Y, so now given any observation, then you can read off from the posterior. Just that all this live in a high dimensional space. Right. So this idea, of course, has come a long way. You think about this idea that we do not need to write down the likelihood and use a surrogate for the likelihood is not new. In fact, in the 1990s, there are not many old people here. So probably not many people will remember. In the old days, people talk about this, right? If you heard of things like ADC, that stands for the approximate deviation computation. They are all in the context of approximate a likelihood. In fact, in the early day of Gen AI, people love to think about that, but nothing works, right? So for example, even in the 2017, 2018, when something called GAN became quite popular, many people have quick to adopt GAN to do science. Short answer, don't use GAN, because there is really something that's really bad about these old models. So what GAN is stands for generative adversarial network. If you do not know, it's just meaning that you have these are two models. One will try to generate the images, and you have another that tries to discriminate, to separate the two. So it's like a Turing test, but by the machine. So you have one guy that tries to generate, and one trying to catch the generation. So this is not a very good idea, because for a GAN, there is really no motivation to capture the entire distribution. If I can make, I don't know, like Josh Clooney, like really well, I will just keep making Josh again and again and again, because that will pass the adversarial test. But does not mean that the machine is able to generate all the human faces. Very simply, if you think about it in the distribution sense, that this is what we call the mode collapse, meaning that you are capturing a tentacle of the distribution. This is why, like, when people are really big in GAN, I always make fun that if you want to have 1% the cosmology, try GAN, you will get 1% cosmology. It does not mean that you really get 1%, it's just that your surrogate for the likelihood is not capturing the cosmic variance of the simulation. So this is a big worry, and people do not believe that this could work until, like 4 or 5 years ago, there is a slew of new ideas that come out in machine learning, mostly on the normalizing flow and diffusion models that become quite popular. I will not get into the technical details here, because that could be 2 lectures by itself. But the point here is that all these methods tend to be very resilient with mode collapse. You can actually mathematically show that it's actually very resilient to mode collapse. So like not too long ago, 2 years ago, I started to work with some students to quantify the differences between GAN and diffusion models and normalizing flow, to show that yes, that GAN is really bad. It has a loss of mode collapse. You drop the loss of the cosmic variance. But things like diffusion models actually is pretty good to the truth. You are capturing the true distribution, and therefore you should be able to trust the fact that up to some unknown systematic, you should be able to do proper inferences using Gen AI as a surrogate for the likelihood. So this is why people, when I started to give this talk 2 years ago, the SBI is not a thing, and people love to hear about that. But if you go to a cosmological conference, people just drop the mic and say, I use SBI, and they just go away, right? This becomes really common now. If you work in cosmology, this is something that people do believe you can do. But if you're just looking at the cosmology, that will not be super interesting, because as I mentioned, cosmology is not super non-Gaussian. You can already do very well with human heuristic. You can even do that even better with things like the scattering transform. But what is really exciting about the SBI is that, as I started earlier, you can start to do inferences on things that you couldn't do in the past. So there are lots of examples, from my student and postdoc that are in that category. But I want to show you one example that I like, which is to understand the merger of galaxies. Most of you are astronomers. I was expecting some computer scientists. For computer scientists, what is a galaxy merger? If you think about that, it's like Dragon Ball. You merge small guy and become a bigger guy. So now you have the bigger guy, and you want to figure out what small guy make up the galaxy, right? You want to figure out what are the progenitors that make the system. But if you want to understand the progenitor system, it's actually a difficult question, because the native way to think about the progenitor system is not an image, it's a graph. You don't care about the images, but you care about the relation between the galaxy and the properties between that. Then you say, well, how do I even do statistical inferences with graph? Because graph seems to be a very hard to define mathematical object. It's very hard to do, thinking how to do that statistic in the past. Unfortunately, or unfortunately, COVID happens, so people care about making graphs, because if you make graph, you can make a lot of money. So this is why with a student, we started to use some of this idea for Gen AI for graph, trying to apply that to astronomy. Interestingly enough, this student also went off to join a biotech company that made a lot more money than me now. But back when he was still a student, we actually looked into learning the conditional distribution between the outcome galaxy from the progenitor system. So here in particular, we are looking at, based on things that we can probably measure from IFU, to some of these properties of the endpoint galaxy, to figure out what are the progenitor systems that could make such a galaxy. So this seems like a bit fuzzy, not super clear, but like conceptually, it's not really that different from cosmology. If you think about in your hydro simulation or like illustrate, for example, of fire, you have some progenitor system at high redshift, you have some output galaxy in low redshift. So you have many such input and output pair. This input and output pair will become your X and Y. What you try to do is only capture the distribution in this input-output space. It's just that now your input is a graph, which is like something that needs some thinking to get used to. But once you have learned the distribution, then if I want to ask what can make, say, the Milky Way, I can just prompt the system and come up with all the progenitors of system that can make the Milky Way. And this, of course, can also be used for the likelihood and try to infer the posterior. So when we started this project, my goal is to understand what can make the Milky Way. So from the present-day galaxy to understand the progenitor. But with James Webb, the other direction is equally interesting. Now you observe something at high redshift, a bunch of galaxies. You can figure out what the galaxy would become after they merge. Right? So this is something that is really hard to do that with simulation. Like if you're just looking for the closest analog in the simulation, you will never be able to find the exact match. So the difference is kind of like, do you still use Stack Overflow or you use Chat GPT? Right? It's a prompt answer, it's a question and answer pair. But GPT in a Gen AI model it summarizes the distribution. So now you can actually prompt in the exact way that you want. If you just look up for Stack Overflow, you don't always get the question that you want to ask. Right? So in sort of visually speaking, this means that you can read off y and given y, read off the function text. In this case, we also apply to simulation and test if that works. So for example, here we assume that you observe some system at redshift of 2, a bunch of galaxies with their masses and so forth. And then you want to predict what the galaxy would become at low redshift. So the crosshair here show you the ground truth because it's a simulation, so we know what the galaxy has become. And the white contour here show you the posterior that we sample. So we actually can sample the posterior if you believe your simulation for any system that you observe at high redshift. You can also sample the posterior of what the galaxy would become at low redshift. Importantly, this idea can also be applied to doing the other direction, right? Just like ChatGPT, you can ask, can you write this email be more polite or less angry? This is the same idea. Like if you don't like your galaxy, you can say, well, how do I make a smaller, more matter-poor galaxy? How do I make a galaxy with a larger black hole mass? You will find the closest analog based on a system that could make such a system. So this is the power of extending statistics, right? So in this case of study, even though this is proof of concept, in the previous case, no one can do parameter or inferences at the level of doing like a posterior for graph. But now we have Gen AI as a surrogate for the likelihood. If you don't care about like parameter like estimation, you should care about outlier, right? A big part of like astronomy is finding outliers. So one of the corollary of Gen AI is that once you have summarizes the knowledge to be a distribution, then you can decide if something is normal and if something is outlier. And the fact that we can describe distribution in a wider range of objects help us to be able to find outlier in the more unconventional configuration. So to give it an example here, so let's say you have all galaxies to be pretty normal. They all look like a normal galaxy by all measure, but putting them together is not normal. The configuration like itself is odd. How do you find such a system? In the past, there's really no way to do that. You can hope that you can pinpoint something is odd or not. But with Gen AI, you can, because now you have summarizes all the progenitor system as a graph. You can ask what is the likelihood of the graph. So as a proof of concept, here we take the illustrator simulation, and we assume that we are some alien civilization. We can move a galaxy. We just move the galaxy left and right. And you see that the Gen AI will actually assign a very low likelihood to the system when we move the galaxy. Because even though individual galaxy looks real, but the combination, the configuration of them is unreal. So this opens up lots of ways to think about like outliers. like abstract. I lost my students to JP Morgan, so that's another question. So summary. Yeah, it's a sad thought. Okay. I need to recollect myself. So the modern day survey is exciting. We have a lot of data, but with more data, what is important is that we are observing more non-Gaussianity because we are having a higher and higher resolution of the data. The classical way of doing statistics is obsolete because if you just rely on the power spectrum, there is, especially outside like cosmology, there are not much to gain because a lot of the system is non-Gaussian. That is, it's very hard to do the statistics. On the other hand, especially for young students, I really don't want you to think that deep learning is just some dark voodoo magic with alchemy. There is a very useful tool, but there are also a lot of beauty behind that. First of all, there is a lot of the mathematical beauty behind that to understand the connection between a summary or statistic with deep learning. But also, the other thing is that with all this Gen AI, it opened up way to find outlier to do the inferences that we couldn't do in the past. So with that, I will stop and take any question that you might have.
Yeah, I think I'm taking over now, Stella, she's running to the airport. So if there are questions, feel free to raise your hand. And for those online, I can see the Zoom hands, so I can call on you if you have a question online.
So thank you for the talk. So you're using mostly simulation to train your either generative model and the inference model, right? Yeah. So are you putting too much trust into your simulation?
No, but no. Yes and no. The thing is like for any inferences, you always have the systematic, right? Even you use very classical statistic like power spectrum, you will always have the systematic that you need to check. So like what you really want to make sure is that most of the inference that you do is out of domain. You train on simulation, you apply to observation. But the best you could do, even before AI, what people do is that you run different simulation with slightly different assumption, and see if you can do out of a domain inference. And this has not changed. Just the fact that our simulation is not perfect means that we still need to do this systematic check, blind test. So a lot of inferences really is not about the fundamental has not changed. We still need to do blind tests to understand how much of the different systematic is changing on inference. The method will not change that. The method just open up more way to do the inferences.
So are you incorporating all the systematics into your simulations as well, the ones that you're showing?
You try to include as much as possible, but of course it's never complete. That just like now the cosmological simulation is incomplete. Of course, you will test on out of domain simulation. But the same thing is to say it's right that the SBI is more they are a fine line to walk because I thinking about power spectrum and cosmology, people can just cut out some scale, right? And say, I don't believe my baryon physics is correct, and therefore for k equals to bigger than x, I will not use that for inference. But when you capture so much information in one black box, it's hard to disentangle each of this. That is a caveat, right? So that is true. I'm not disputing that is true. But the thing that people are doing SBI in cosmology is still exactly the same. They run different simulation, claim on one and apply to the other. Yeah.
Your scattering transform is very powerful for picking out a signal in, for example, parity violation compared to other methods. Does that power also increase the rate of false positive detections?
The power, not really. I mean, I don't think that why that would be the case. I think this is tied to the question that because if you think about scattering transform, you're still doing some bandpass filtering and doing some operation. So it's very easy to check where the information comes from. If you know that this is small scale or the clustering of small scale, then you can check that. So this is still one of the my position has been if I can do this type of signal processing, I will do that because I know what information and what scale I'm picking up. This is why this is another advantage to do this type of analytic deep learning inspired analysis. because it's really not that different from our spectrum. You know exactly what wavelength band you are capturing the information.
There is a question online that says, I wonder whether AI ML can help us have breakthroughs on dark matter and dark energy. If so, when and how?
Of course, the short answer yes. But this is sort of the thing that is tricky, right? So if you think about like DAISY is a good example. So DR2, they are using the power spectrum for the release because this is something that we are really well studied. We understand the systematic extremely well. People are doing like alternate statistics, and partly because, as we discussed, like cosmology is really just weakly non-Gaussian, right? So this is why a lot of the information is already in the second moment. So this is why you can get a lot like information there. So this is why people are happy that to say put this out like the second moment, the power spectrum, and have the constraint. So we get a 4.2 like sigma, like tension with whatever models. Of course, if you do like alternate statistic, it could be a scattering transform, it can be simulation-based inferences, it can be bispectral. You might push that to like 5 to 6 sigma. That could be important, right? So sometimes you need to convince people from 3 sigma to 5 sigma. That would be the differences. But cosmology is always like you will try to squeeze out as much information as possible, but it comes with also the trouble of checking your systematic. I don't necessarily believe that using more information will lead to more systematic, because I feel like even in the power spectrum, there is also like the systematic to be checked. But there is a fine line. Right? This is called the modern day trolley problem. Do you Q1 or Q5? Right? If you want to get more constraint, you will lose some of the understanding of how you do the inference. But sometimes you decide to Q1, and sometimes you decide to Q5, and that is a case by case basis. But I think like cosmology is in the regime where people are really interested in squeezing out as much information as possible to find any like deviation from the physics. So this is why a lot of people are doing the alternate statistic to really squeeze out the information. Yeah. For example, you know, like galaxy, who cares? You know, do I care about like constraining my halo mass from like 1.1 to 1.102? It does not like matter. But with cosmology, it can matter. So this is why AI usage SPI is very case by case basis.
Would you say one of the reasons for this scattering transform is it capture symmetry is better, or do you?
No, actually, the reason that you can look at the operation here, if you dive deeper, so one thing I didn't mention, like we explained the nonlinearity and the pooling. What is really interesting is the wavelet part. The why people do wavelet and how do you really use a low dimensional single wavelet to analyze the whole map. So ultimately, what is being assumed is, for example, in big lensing is a scale invariance. So you use the same wavelet at all scale. So this is why you can like use a very simple operation that apply to many things. And this is something that works really well for cosmology. And this is why when you try to do something that is slightly non-cosmology based, even for the parity violation, we use a lot of the tuning on the wavelet. So there are some what we call inductive bias. So for any machine learning model, it comes with a set of assumptions. In the case of the scattering transform, is more harnessing the fact that the universe at large scale is scale invariant.
There's another online question. There are many noises or sometimes even unknown systematics in our observations. If we use these data to train a generative AI model, how can we evaluate the accuracy, robustness of the Gen AI model? That can be important for knowledge discovery.
So generally, for inferences, you always tend to want to train Gen AI on simulation. Because of the same reason. There are lots of correlation that can be being like induced in the data. And that will create a lot of spurious correlation. And you and I know like really well. In some cases, we have to use data-driven models, but we really don't want to use that if we don't need to. Exactly because it will create a lot of the spurious things. There are ways that there are mathematical ways to decouple that, but that is just like in theory it works, but because we never know all the systematic data, that's quite difficult.
I had a question. Thank you for the good talk. I was wondering, it was interesting to see how you mentioned these deep generative models being an avenue for sort of tackling these nonlinear regimes, but I'm curious about your thoughts on where they may still have shortfalls and where they may still have issues, and whether those are sorts of things that can be fleshed out with the current strategies that we have, like you were talking about normalizing flows and diffusion models, or whether you think that in the long run there will have to be new generations of models or strategies developed in order to tackle the shortfalls that exist with deep generative models.
I think conceptually there is no bottleneck. So, but I think the idea here is that if you just run a normalizing flow diffusion models without any additional assumption, it's very data inefficient. Because if you make no assumption on the distribution, it really means that you need a lot of data to capture all the jellyfish in like distribution. So in physics, it's not the case because physics is very like a regular. So a lot of the effort now people are doing in diffusion models is really trying to make more assumption to the distribution. You can include some of the symmetry, you can include some of the PDE that you know has to be true. That is just a form of regularization to make sure that the distribution is more rigid. Where are you, God? And to make sure that you can train with a smaller number of training data. So there's always at least like more. I think one of the shortcoming is that is the lack of what we call inductive biases. So this is why it's very data hungry. Like compared to like when you make a very strong assumption, you need very few data. If you make less assumption, you need more data. Right? Take the limit of linear regression, you can fit one line with 2 points. You can exactly know that line. But if you fit more like flexible models, you become more and more data hungry. But it's unclear that why physics needs that much like training data. So this is why it's all about including more assumptions that you know to be true. But that open up a lot of like little thing that is interesting. For example, like how exact your symmetry is. This is all like weak inductive biases. That is a very interesting field of research.
Great. Since we just hit the top of the hour, I think we'll go ahead and close there. Thank you all for joining.